So in this particular case, one of the compilers found that there was a problem. Yeah? Is that GCC or Intel? It was Intel, that bad Intel compiler and so on. Yes, it couldn't find the problem. So, so depending on what the actual dependency is, sometimes you'll find one compiler spots that you can find a way around a dependency, and sometimes another one will. And sometimes neither of them will. But if one of them does, it means there is a transformation that you can make. And if you can discover what it is, if you can see it, then it's helpful. If you get a hint, if it's Intel that's having difficulty, but might think that there is a way around it, I don't think it did in this case, but it might give you a hint. If it's GNU that was the one that could do it, unfortunately, it's more difficult to see what's doing. Other compilers may also show you what they do to transform things to help the vectorization. But at least you know there's a possibility of winning. In this particular case, with Intel not being able to do it, but if you split the main loop in two, because they were separable loops, you then found that, okay, it would vectorize, yes, and then give you a better speed up. But as a few people down here were saying, but if you have that piece of code, then GNU slows down. So it's not very helpful if you've got to choose one of those particular ways of laying out your code, because you've also got to choose which of those two compilers you want to be the winner in that particular case. That's part of the pain you have to go through, I'm afraid. So, so to summarize what we've just been looking at then this morning, so we've seen that even on our established processors, after all, this is an Intel Westmere, this is year 2 old now, and we have Sandy Bridge processors with even more vectorization, or even wider vector registers, even more difference between the vector and non-vector code, and moving forward to the Intel mic. We've already seen we can dramatically improve performance on some floating point intensive loops if we've already done the optimization for the cache, which, as we said at the beginning, that was artificially squeezing this problem down so we don't have any cache effects. There are, as we saw, a number of factors which inhibit vectorization. Some of them aren't necessarily going to be there on all processors or all instruction sets, I should say. And some of them are also not on all compilers. The vectorization reports are useful. Hopefully you've found them useful, and a guide as well that can be useful. You've seen that one compiler can fail to vectorize where another can succeed, but at least you know, therefore, there is a way of vectorizing if one of them can succeed. And succeed doesn't mean that it just says, I've vectorized it, but it actually delivers a speed up. And as we said, the Intel compiler can provide you with advice on how to change your code to help it to vectorize. At the moment so the way we wanted to progress through this was look at single core issues, which is the really important one. You've been doing parallel programming this morning, it's just that you've let the compiler be doing the parallelism for you in the vectorization. And then we look at some caching effects, and then we look at threading, and that's David's going to be doing that this afternoon, or it's going to start just after this session, but just before lunch, and then move on. So that's where the parallelism will come.